So we're going to do a few more examples of area and polar coordinates, starting with this one. I believe it's called a lemniscate, is the correct term for something like this, a region like this. Now, as a quick reminder, the formula for the area and polar coordinates looks like this. It basically derives from the trigonometric formula for the area of a sector. Now, in this case, we're kind of lucky because we're already given r squared. R squared equals sine of 2 theta. The question is, though, all right, well, what are going to be our limits of integration? And that's where I want to spend a little time on with this video, is finding those limits. So in particular, the curve is going to be integrated so that we have limits to go between 0 and 0 for r. So the question is, well, when is r equals 0? And that's what we have to start out by answering. So let's look over here. We've got 0 equals sine of 2 theta. If you wanted to get theta by itself, you could take the inverse sine, also known as the arc sine on both sides. Now the arc sine of this is going to cancel, leave me with 2 theta. Now you might say, well, all right, I know where sine is 0. Sine is 0 and, theta equals 0. And that's fine, but we need a little bit more general solution here. Sine of theta is going to be 0 whenever it's a multiple of pi. So let's just call this n pi, or 2 theta. You could see that if you looked at a quick Desmos graph. Let's take a quick look up here. Open up a Desmos graph and graph y equals sine of x. Y equals sine of x. So if you needed to remind yourself where sine is equal to 0, it's going to be at 0, pi, 2 pi, 3 pi, 4 pi, basically multiples of pi. So that's where we get this. N is just taking the place of an integer. Now if I divide both sides by 2, I get n pi over 2 equals theta. We can make ourselves a little table of values here to figure out, all right, well, when this is going to be 0. Now, I'm not going to go very far down this list because we don't need to. So we have values for n, we get values for theta. We'll start out with n equals 0. If n is 0, then theta is 0. If n is 1, then theta is pi over 2. And that second term should be it. Between these first two terms, we should trace out one loop of this graph. That's what we're counting on. So let's take a quick look at this graph. What we want to do is figure out, well, how far do we go to get one loop? And as you can see, as I rotate around, when I get close to pi over 2, then you're going to get close to going one loop around. Is that a proof? No, it's not really a proof, but it's convincing enough to help us feel that we're right and moving forward. So the limits of integration then are going to be between 0 and pi over 2. So to find this area then, it's going to be 1/2 the integral from 0 to pi over 2 of sine of 2 theta d theta, like that. That's something that I hope you can solve. Maybe kind of a challenging Calc 1 problem, but for Calc 2, should be no big deal. And here it is all worked out. Careful at the end that you have a double negative, and the negative times negative is what gives us a positive answer. You should expect a positive answer for these types of questions. All right, let's move on to another example. We're going to roll off several of them real quick and get you on your way. So the next one is, again, kind of challenging if you don't have the right software or the ability to visualize this. So we've got another lemniscate, and this time it's stretched out a little bit. Want to find the region that's common to both that lemniscate, the first equation, and r equals 3. R equals 3, I hope you recognize, is just a circle of radius 3. It's a really simple equation in polar coordinates. So it's kind of nice to work with polar coordinates for some things, especially like circles. So let's take a look at the graphs for this one. And here we go. So we've got our lemniscate and a circle. We want to find the area that's common to both. So that's going to be the area in here and down in here as well. Now finding that area is going to present a little bit of a challenge. So let me just zoom in on half of it and talk about the challenge. What you have to keep in mind is how area is calculated in polar coordinates. It's not like a bunch of rectangles as it was with Calc 1. In polar coordinates, you've got these little triangles that are kind of mimicking a sector, and they emanate from the origin and stretch out towards your radius. So let's rotate around A a little bit, and you can start to see it, but let me zoom in a little bit more, try and make this a little bit more dramatic. And there we go. You can start to see that coming around. But there's a challenge here for us in this problem. At this point, we have to change curves. So I want this little area from the red curve, and then I got to switch over and get an area from the blue curve. So what's that area from the blue curve? Well, that's going to be this part right here. And between these two areas, between the red area and the blue area, that's going to be 1/2 of this region in the first quadrant. And of course, we got another region in the second quadrant. So if I could find this area and multiply it by a total of 4, then I'd be in good shape. But the first thing I have to figure out is where those two curves intersect. So let's work with that. So this is example B. Example B. And for example B, we had r squared equals 18 sine of 2 theta. That was one curve. And the other curve was r equals 3. Now to find where they intersect, I've got to set those equal to each other. So in particular, to set these equal to each other, it'd be helpful if I had r squared here. Well, that's pretty easy. R squared is just 9. And now I can set these two things equal to each other because I've got r squared here and r squared here. I've got different expressions for r squared. So let's set them equal to each other and solve. 18 sine of 2 theta equals 9. Divide both sides by 18. So that gives me 9 over 18, which of course is 1/2. So sine of 2 theta equals 1/2. To solve here, I can take the inverse sine on both sides. So that would be like this, sine -1 and sine -1. These two operations cancel each other out. The inverse sine of 2 theta cancels, so I'm just left with 2 theta equals the inverse sine of 1/2. Well, there's lots of different answers to this, but I think that we want just the first one that we come to. First place that has a sine, a y-coordinate of 1/2 on the unit circle is pi over 6. But that's 2 theta. If I want to know what theta is, then I got to divide both sides by 2, or it's probably easier to multiply by 1/2. So if I multiply by 1/2, that cancels, and I'm left with theta is pi over 12. Yay. So that's the point where those two things meet. So let's take a look back at our graph. Now on Desmos, if you'd like to, what you can do, it's kind of nice. is switch from a normal grid to a grid in polar. And that's kind of helpful because it certainly seems to confirm some of our intuition that, for instance, this is pi over 6, and halfway between 0 and pi over 6 is going to be this point right here, pi over 12. So the first integral is going to be the integral of our function 18 sine of 2 theta between 0 and pi over 12. That'll give us that little piece. And then the second integral is going to be the integral of 3 between pi over 12 and pi over 4. And then you got to take your results and multiply them by 4. But that's the basic setup, is those two integrals. And hopefully you followed me along with where the intervals were set up from. So we've got two integrals here. Each of them gets multiplied by 4. And the rest is just a little bit of work with integration and some cleaning up. But the hard part, of course, in this one is to figure out, where do I set these things up? What are my intervals over which I integrate? Two more examples. So let's go to example C. Example C asks us to find some points of intersection. I want to find the points of intersection between these two curves right here. No, that's not what I want. Let's try it again. These two curves right here. Now, they do something kind of annoying here. If the curves intersect at the origin is called the pole, then that's going to be one of your points of intersection, and you're actually supposed to type that out as pole. And that one has to go first. And then you got to order things in smallest to largest in terms of theta. Of course, this is being done on WebAssign, so a little bit extra annoyance. But let's take a look at the graphs here and see what we can see based on the graphs. So, is this the right one? No, it's not the right one. My bad. Let's shut this off and come down to here. So you should see two cardioids like that. And as before, if you want to, you can adjust this. I'm going to put it in projector mode and also change the grid. It might help me to zoom out a little bit. There we go. So we can see several points of intersection. Our job is to find those points of intersection. One of them looks to be the pole. Indeed, these two graphs do both touch upon the origin. But there's a point of intersection here and another one here. Let's see if we can't find the coordinates of those points and what value of theta they occur at. So to that end, let's work out example C. We've got our two equations, r equals 1 minus sine of theta, and r equals 1 plus cosine of theta. These are cardioids. It's about as romantic as math gets. Actually, that's not true. There's some nice applications of math, including romance. But let's set these equal to each other and solve. So I get 1 minus sine of theta equals 1 plus cosine of theta. I'll subtract 1 from both sides. Let me pull out my calculator here. Oh yeah, 1 minus 1 is 0. Thank you. So I get negative sine of theta equals cosine of theta. Now there's a couple different ways to do this. I'm going to do it a little bit different than I'll display when I get back to OneNote. but I'm going to divide both sides by cosine of theta. Negative sine of theta divided by cosine of theta, and cosine of theta divided by cosine of theta. The nice thing is that on the right-hand side, I get a 1. And on the left-hand side, instead of dealing with 2 trigonometric functions, I can deal with 1 trigonometric function. And that 1 trigonometric function is tangent of theta. If I divide both sides of this equation by -1, there you go. I get tangent of theta equals -1. You may remember from trig that there's a couple places where that's going to happen. In the unit circle, it's going to be in the the second quadrant and the third quadrant. Yeah, I lied. Fourth quadrant. So much for my nice neat circle. But the values where tangent is equal to 1 or -1 are going to be multiples of 45 degrees. So remember, all students take calculus. All of our trig functions are positive in the first quadrant. Sine and its reciprocal are positive in the second quadrant. Tangent and its reciprocal are positive in the third quadrant. Cosine and its reciprocal are positive in the fourth quadrant. And we've got to find where tangent of theta equals -1. As I just said, tangent equals 1 and -1 along these lines. This is not the only way you can get at this. You can look at a graph on Desmos as well. You can graph tangent of x equals -1, or tangent of x is one function, y equals -1 is the other function, and see where those two things cross each other. But basically, for our purposes, we need 2 solutions. One of them is at this point, 3 pi over 4. And the other one is at 7 pi over 4. After that, things are just going to start repeating themselves. Now, if you take these 2 points and plug them in here, you'll find the points of intersection. So let's just do one of them. So at theta is 3 pi over 4. It's going to be r equals 1 minus sine of 3 pi over 4, which is going to mean 1 minus sine of 3 pi over 4 is going to be square root of 2 over 2. So that's going to be your r. And as far as an r and theta pair are concerned, it's going to be 1 minus square root of 2 over 2 and 3 pi over 4. Now to finish this one up, just plug in theta up here as well and get the remaining point. I'll give you a hint. Cosine is negative in that quadrant. All right, one last final example here, and that's this one. Just like our regular functions, just like parametric functions, we can still deal with arc length. For arc length, we're going to use this formula, integral of a to b of the square root of r squared plus the derivative of r squared, and take the square root of that, and you should be good. We're going to demonstrate that with r equals cosine of 2 theta. So not too harsh of an example. Let's again look at a graph, and I'm hoping I have that one up and ready. Nope, I don't, my bad. So we'll shut this graph off and turn on example D. Now what you see here is kind of a clover shape. We want to find the arc length of the entire piece. Just like before, the challenge for you is going to be to figure out, well, where do I set up my integral? I'd be cautious about just doing 0 to 2 pi. Sometimes if you do stuff like that, funny things happen because there are points at which the derivative could be 0, or excuse me, derivative could be undefined. I don't think it's going to be the case in this one, but what we're going to do is we're just going to look at part of this. So if we can figure out an interval that goes from here to the origin, then that's going to be 1/8 of my entire integral. So that's one possible way to work this one. Another possible way to work this one is just to pick a pedal and do 4 times this area. So either one works. So kind of up to you. What would you do? Okay, that's fine. We'll do that. So we'll stick with this one and do 8 times the appropriate integral for this one. So let's get back over here. So we've got R was cosine of 2 theta. If you notice on the exam, I kind of avoided cosines like this a little bit, simply because when you differentiate them, you need to remember that you get that negative sign. So it's going to be negative sine of 2 theta times the derivative of the inside, which is 2. So there's your dr d theta. The big question is, where do I integrate? And I'm going to integrate starting at 0, because at 0, you're going to be right out at the edge of your clover here, and it's going to start coming back. The question is, how far do I have to integrate to get back to the origin? So that's going to happen when cosine of 2 theta is 0, or 2 theta equals the inverse cosine of 0. Now the inverse cosine of 0, the first place that cosine is 0 is going to be pi over 2. And if you multiply both sides by 1/2, then you'll get theta is pi over 4. So that's telling you where the function comes back on itself. Theta is pi over 4. So that's good. I can now find this integral. So its arc length is going to be a total of 8 times the integral from 0 to pi over 4 of the square root of cosine of theta, cosine of 2 theta squared plus, running out of room here, negative 2 sine of 2 theta also squared. That's still underneath my root here, and then d theta. So sorry about a little bit of a mess there. One important thing that you need to keep in mind as you do a problem like this on your calculator is that you got to have your calculator in Radian mode. So let's take a look at our TI and clear out some stuff here. So we'll check our mode. We are indeed in Radian mode. So that's good. Let's clear this out. And you can follow along with the keystrokes here. We're going to start with math 9 to go from 0 to pi over 4. So second up arrow divided by 4. Right arrow takes you into the integrand. I'll start with the square root. And unfortunately, it doesn't recognize the cool notations that we can use. So you need parentheses around both of these terms. parenthesis, cosine. It puts in the left parenthesis, cosine, let's do 2x, not theta. Oh, I must be in parametric mode, yeah. So it's giving me a t instead of an x, that's fine. I need two right parentheses. The first closes off the cosine, the second closes off, or first closes off the argument of the cosine, the second closes off the cosine itself. Then hit the squared key plus left parenthesis, -2 sine of 2t. And I didn't really need to put in the negative. I did just because that's what we had written down. Again, I want to hit the square key, exits the radical, exits the root, or excuse me, exits the integrand, and we'll throw in our dt. Now we're not quite done with that. We've got to multiply this by 8. So times 8. That'll take your previous answer, multiply it by 8, and now we're good. So if you take a look at this a different way, an alternative approach would be to integrate between -pi/4 and pi/4. Again, that gives you like one whole leaf. You'd have to take this answer and multiply it by 4 to get the area of the entire figure. So like I said, a different approach would be to find the area of one whole leaf and then multiply it by 4. Awesome. Hope this helped. Good luck with this material.